Okay, hello everyone. Welcome to the latest edition of this UK Metamaterials Network seminar series on AI for metamaterials. So today we're delighted to have Dr. Rahele Kafieh join us from the University of Durham. So Dr. Kafieh has over a decade's experience of medical data image processing using AI, but today they're going to give us a talk about metamaterials. So the title is AI applications and different data modalities for metamaterials. And we're all looking forward to hearing what you have to say. So thank you very much for being here, and over to you.
Thank you very much for the invitation. Well, before starting, I just want to confess that I'm not a professional in metamaterials, as you kindly said. So please accept my apologies if I use a term incorrectly also. I would like to talk about application of AI in different data modalities, and actually the emphasis of this talk is how to find which AI model is the best, the perfect match to the modality of data that we are going to work with. So just to start, I just want to give a kind of warm-up introduction to artificial intelligence, machine learning, and deep learning in a way that we will use it in next slides. Well, as you all know, artificial intelligence is teaching the machine to think without doing any human intervention. And for example, imagine that we have a kind of machine that can play chess based on some rules. It does and replicates and mimics the human intelligence. And this is the perfect AI that we expect. As a kind of subset of AI, we usually talk about machine learning, in which the computer program derives the rules from the data. And the most important thing to consider in machine learning is that the features or inputs to machine learning should be defined by us. I mean, machine learning is not able to find the best features to work with. For example, if we want to talk about playing chess, we should say to our machine learning methods, what is important? Is it important to look into the location of the chess pieces or consider the movement of each piece? These are important things that we should learn and teach to our machine learning algorithm. From this on, it looks into data and tries to find the rules, but features are not predefined. And deep learning is a kind of technique in machine learning that somehow is a bit more complicated than conventional machine learning methods. And the most important part is that the same features that we were talking about can be found automatically. Therefore, there might be some pattern in our data that we couldn't even see. An expert didn't consider that, but deep learning methods can exactly extract that feature and use it in downstream applications. So, for example, we have a machine that looks into the chess playing, a video, a couple of images or so, and doesn't need us to say what is important in this play. It finds the feature so it can go on and understand how to react the current game. So we usually deal with convolutional neural networks as the most important subclass of deep learning methods. So what happens in convolutional part of the network? As you can see from this image, in the left part, the convolutional part is in charge of feature extraction. Therefore, that specific term of extraction of features happens using these convolutional layers. And as soon as the flattened line in between, as you can see, extract the features, the next step, the place that we call the fully connected layer, is actually a machine learning method. So in deep learning methods using CNN, we actually have a part to extract features. This is the convolutional part, and we add some machine learning method after that to use those features for different tasks like classification, regression, or so. And what is this convolution? This convolution is a kind of mathematical operation that applies a kernel or information of filters into different parts of our image, signal, everything that we have. And it produces a feature map, as you can see here. And this feature map can go to the next step as input, and we do again the same convolution process, and over it happens. So the most important thing about deep learning and convolutional neural network was first that they could extract the features automatically. And second, is looking into this shape, you can see that this kernel or change preserves the lateral information of the data. So for example, imagine that we want to compare some data points with a kind of signal or a kind of image. And the main difference between data points and an image is that in an image, I expect a kind of lateral information in X or Y, Z. So the points or the pixels are not separated. They have some relation to each other. And CNN methods using convolution can preserve this information. So it's really important to consider if our data sets are not separated, our data points are not separated and have a kind of relation, it's always better to use deep learning using convolutional kernels rather than just using machine learning that deals with everything just like a vector or points that have no relation to each other. Well, so to consider the learning methods in machine learning, we have three main categories: supervised, unsupervised, and reinforcement learning. Talking about supervised and unsupervised, as you always know, supervised learning is a process in which we show instances and try to actually learn or train our algorithms using those instances. So we show a kind of duck and we say, yeah, this is a duck. And we show other animals and say, this is not duck. And we expect that after showing lots of data, our model is enough trained to see an image to say if it's a duck or not. So we need a lot of data to train our supervised algorithms. But on the other hand, in unsupervised algorithms, the algorithm looks at the data, infers the pattern, and we don't need to provide the noun labels. So depending on our application, we should decide which one to use. If we use a supervised learning algorithm, we should somehow separate our data and have a training and test set, and we have something like validation set in between. But to talk about training and test, we provide the training set with labels, with information to our model. And after that, our model is already trained and finished. We can expect that for each test data, it produces the prediction that we expect. So the process can be classified into two main steps. Looking into applications of supervised learning, one of the well-known ones is classification. Well, in classification, what happens is that, for example, we give some features and expect to see if the weather is hot or cold tomorrow. So it's a binary classification, or we just want to see if it's sunny, windy, cloudy, rainy, snowy, or so. So it's a kind of multi-class classification. So one of the main applications is classification. The other one is regression. And in regression, we just want to get some numbers rather than classes. For example, we want to know how is the temperature tomorrow. So we use different models for regression. And finally, we may look at as a kind of segmentation that's mostly worked in image data. So we want to say, where is the cloud? Where is the sun? Where is that cat? Or where is the abnormality in medical images? And lots of such information. So these are samples of supervised learning types, and they all need a lot of labeled data to provide it to our network before training that. But what happens in unsupervised learning? In unsupervised learning, we actually don't have the specific target. Therefore, we only have the data. And the algorithm should discover the pattern itself by data grouping or so. An example of unsupervised learning is when we have a baby and she or he knows the family dog, but hasn't seen any other dog. When a few weeks later, a new dog comes, the baby can somehow find that it's a dog without that we will tell him or teach him, train him that it's a dog. He finds some similar patterns, let's say 2 ears, eyes, walking on 4 legs, the face, everything. And well, it is her pet dog. He can easily find the answer. So this is not taught. Otherwise, we should get, as soon as we would bring the dog, we should say her, oh, it is a dog, and it's the kind of introduction, but doesn't need that step. So if we don't have the labels or we don't know the patterns, it's good to use this unsupervised learning and wait to see if it can find the information hidden in our networks, hidden in our data, and it can work on real time. Well, it doesn't need any labeled data, so it doesn't need a lot of manual intervention that sometimes is really important for us. But what we can do with unsupervised learning? One of the most important and well-known classes of unsupervised learning is clustering. It's very similar to classification, but it is unsupervised. So I have a data and the algorithm tries to put them in different groups or clusters automatically. So finds the similarity, and this is the reason to put a bunch of data in one cluster. The other unsupervised learning type that's relatively new is generative adversarial networks, or GANs. In GANs, again, we don't have a label. Imagine that I have a bunch of images and I want to produce a new image that is very similar to these ones, but it's not a copy of them. So what happens is that I make a kind of network, we call it generator. And as input, we give it some noise data and we expect it to produce the output. However, how can I be sure if it is good enough and similar to our real data set? So we prepare another network. It is called discriminator, and its duty is just to find out if my produced data is similar enough to my real data or not, and gives the kind of label of fake or true, real. And in this way, our discriminator and generator are adversarial, but they're working together to give us the best performance, and they're producing some new data that is very similar to what we would expect. And finally, another subclass of unsupervised learning types is autoencoders, that we usually mostly use them as dimensionality reduction methods. Again, we don't need any label data. We have a bunch of data, and we prepare a kind of encoder decoder in a way that we expect it produces exactly the same data in output, the copy of data that we give it as input. So I will discuss it a bit later. And this is the way that I expect the information in input and output that are the copy of each other encapsulate in a kind of a small number of data as our features, and we can use it as dimensionality reduction. So talking about these two supervised and unsupervised methods, this table gives a kind of summary to us to say, if the supervised learning is used in continuous data, we expect regression. But if unsupervised learning used on continuous data, we have some dimensionality reduction. Similarly, if supervised learning is used in categorical data, we have classification, and otherwise for unsupervised learning, we have clustering. So this is the relations that we usually expect to see between classification, clustering, and regression dimensionality reduction. And something else in between is about semi-supervised learning. It's a kind of, let me say, like marriage of a hedgehog and a snake, like Biowire. It's something in between. So you would like to have a kind of supervised method, but you don't have enough data. The solution is something like semi-supervised learning to learn some part using supervised methods and learn some patterns using unsupervised methods altogether. Finally, talking about reinforcement learning, actually the main case in reinforcement learning is if you compare it to supervised learning, it doesn't get the set of correct actions. Instead, it just uses a kind of rewards and punishments for training. And if we compare it with unsupervised methods, the main output is that it finds, when unsupervised methods find similarities and differences in reinforcement, actually, they find a suitable action model that maximizes the reward of the agent. Well, talking about those backgrounds, we want just to go into different data modalities and find a kind of match between these modalities and those applications in AI. Again, as a kind of warm up to see what we already have as our data modalities, I would like to come back into metamaterials and to see what kind of data modalities we may expect. Well, knowing that metamaterials are composite materials that are designed and manufactured artificially to interact with light and other forms of energy in a way that's not found in the nature, I can say that the crucial step in development of metamaterials is optimal design of structural units. In terms of their size, shape, distance, everything, and the interaction between them is also really important. And what output are we expecting? It's kind of desired properties. And the question is how to measure all these inputs and the desired properties. By understanding the properties of metamaterials, a kind of inverse design or reverse mapping can be performed. And the case is how to understand the properties. In the first instance, we may say macro scale data can be used. For example, imagine that I'm measuring the properties using some numerical values like measurements of conductivity, for example. On the other hand, some macro-related data can come from signals, like a spectroscopy of the piece of metamaterial that we have, or some visual properties like digital photography. But sometimes these macro scales are not enough, and we want to get some micro or nanoscale information. So we may use something like computed tomography or atomic resolution imaging or IR thermography. And these all provide a kind of image-based data. So starting from that point, data points that had no relation to each other, we go into signal that changes in time or in a space, and therefore the relation between data points is preserved in it. And again, with image, as we discussed a few minutes earlier, the relation in X and Y direction or 3D data can be preserved. And it's a bit different from data points that we discussed first. The other part of the today's talk will go about the graphs and how they can be incorporated in our metamaterials and what kind of presentation a graph can provide for us to actually show the information that we need. And finally, I would like to discuss what happens if I have different modalities altogether, and I want to somehow fuse and use the information from all of them altogether. Well, what happens in AI is that the analysis of different data modalities is already advanced using different AI methods, and actually using the methods that match the best are the best match for our data is the best way to extract information that we're looking for. So the question is exactly this: which AI method should I use for which data modality? And this is what I'd like to have a bit more discussion about. So talking about numerical values, we said that they are data points, that they are separated from each other. There's no relation between them. So apparently, you can use machine learning methods easily, but the reality is that if we have enough data, deep learning methods can also be used. So there was no preference to say, I can never use machine learning methods or deep learning methods in numerical data. But it differs a bit when I talk about signals and images. As we discussed a few minutes earlier, it was the story of convolution that preserves the information, the lateral information. And that's why deep learning methods, particularly CNNs, are very good candidates to analyze our signals and our images. And autoencoders and GAN networks are also good for this purpose, and we will discuss it in detail. Something that is very lovely to talk about is actually autoencoders play a very nice role in between, because sometimes I want to extract features. Okay, so input is signals and images, and we discussed that the good candidate for them is deep learning. But I don't have enough data for training our deep learning algorithm. What I can do? Autoencoder comes and using convolutional methods, but using a small number of data because it's unsupervised and can work with small data, extract some information or features for me. And we discussed that machine learning couldn't extract those features. However, deep learning was able. So autoencoder is something in between, extracts information for us. Therefore, I don't need deep learning anymore, and I can apply machine learning methods on output of my autoencoder. So using convolutional autoencoder and using the information in latent layer as input to our machine learning algorithm is a very wise method when you have some data with lateral information like signals and images, but you don't have enough data to train your big deep learning methods. And when we talk about graphs CNN is a good candidate that we will talk about. And finally, when we talk about multimodal data, we can use many models like machine learning, deep learning, CNN altogether. And we want to discuss these a bit in more detail. So when I want to say which AI method for which data type, I just want to be more specific on metamaterials. So I'm using a part of publications available and want to give examples based on those. So talking about the numerical data, we saw that machine learning and deep learning is a good candidate to deal with. I would like to go to this paper. It's published in 2019. And the input to this network are exactly data points. They are, for example, filling fractions, mass density ratios, or shear modality ratios for phononic crystals or PCs. And what has happened in this paper is using two different machine learning methods like deep backpropagation neural networks and radial basis function neural networks. And both of them are machine learning methods. So the input to them is some data point and output is a kind of prediction. So the output is dispersion relation of 1D piece. It's a kind of regression-like algorithm. So the only thing that I want to emphasize is that how we chose the machine learning algorithm here, we have some data points. Okay, so machine learning will work for us. I don't have a huge number of data, so machine learning is enough. We don't need to go to deep learning and make it very complicated. But what happens if I am dealing with images? For images, for example, this paper is the one that I would like to talk about. It's published in 2020. It has different parts, and I would like to take a look on each of them separately. First of all, the input to our algorithm is a phononic crystal RV samples. They are generated by using various parameter combination images. So we have some images as input. The question is exactly that. These are images. So I need a kind of deep learning method, a convolutional method to preserve the information into axis. So I don't have enough data. I don't have millions of data to train my deep learning algorithm. So why not use autoencoder, extract features, and use a small machine learning algorithm? This is exactly what happened in this paper. They used the input images and the output. This is the same image. It's autoencoder. So we show it as input and output. And autoencoders trained, and as you can see, the big image goes smaller and smaller, and we just have a small number of data. It's a kind of vector, and it's a representative vector. And how can I be sure that it's a good vector? How can I be sure that it has the features? The reality is that in the process of training autoencoder, we expect that output is a copy of input. I mean, if the input can be reduced a number into a bunch of numbers, let me say, topological features. And then if the decoder is able to reproduce my input image exactly without any loss, well, I can say that those tiny numbers, topological features, were enough for me for reconstruction. So from now on, instead of my big images with lots of dimensionality, I can use those latent space of autoencoder or topological features. So this is the feature extraction story. So for example, let me say if I wasn't using autoencoder, I should just talk to a kind of expert, and he or she would say me, okay, the number of the changes in direction of each shape is important, the area is important, or the size is important. And these were the features that would be determined like number of points, but using autoencoder, these features are determined automatically. And then what should I do? It's easily just send them into a kind of machine learning algorithm. A small MLP does the job for me. So they use the kind of FEM, finite element method, to find what is the band gap calculated with those samples. So having the band gap, they trained a kind of MLP, a small machine learning algorithm, which its input is that those band gaps, and its output is exactly the topological features that we found from previous step. So from now on, having a small number of data is enough for training an algorithm to get the input as band gap and produce output as topological feature. And if this process is finished, my training stage is done. So the exciting part is how to use this in designing. Well, I have an anticipated band gap. This is the input to our algorithm. I have two networks, both of them are already trained. The network with machine learning produces the topological feature, okay? And then having the topological feature, I need to know what kind of sample shape I need. The autoencoder is already trained. I just don't use the encoder and just concentrate on the decoder part of the network. Therefore, its input is topological feature, its output the image that I was looking for. So the whole process has the band gap as input, some mid output that's topological feature, and some main output that is the design sample. So in this design step, the trained models are used together and the purpose of the algorithm is found without using a lot of data that was needed for the whole process being done in deep learning background. Well, another example that I would like to talk about is when I have images and signals together, like this paper published in 2021. First of all, let's see what was the GAN. We talked about it. The generator was getting the random noise and producing some images, and the discriminator was comparing these produced images with some input data to be sure that they are similar enough. And in the final process, they are in a kind of adversarial networks. And finally, we expect that generator is working too good in a way that discriminator cannot find if the produced image is real or fake. As soon as the discriminator fails, the algorithm is finished. So it doesn't have any labeled data. We just give it a bunch of input images. So the problem is that if I give a lot of images, it produces some data, some image that is similar to all data set, but it doesn't have any specific properties. What happens if I want my generator to produce a data with specific properties? This is when a conditional GAN comes through. So I have a condition, a specific condition, and I give it with random noise to my generator, and also I provide it to my discriminator. And in this way, it somehow ensures that I produce a kind of sample that has the specific condition that I was looking for. So let's see what happened in this paper. First of all, let's talk about the bunch of data input images that we had. The input images were just synthetic training data by using the random generator algorithm. So these were as input. Do we need any output? No, it is GAN, and we discussed it's unsupervised, so we don't need any output. And it just tries to produce the data. However, what is the condition that we are talking about? The condition in this paper was a kind of finite element simulation on input images that would produce the transmission loss. This is a kind of signal. So this transmission loss is something that we want to guarantee that our produced images using generator have the property. So this is the whole story that was done. The GAN proposes a cell candidate regarding the desired transmission behavior of the metamaterial that we are looking for. And if you take a look into the outputs, you can see that generated cell designs have the transmission properties that was desired for the network. In a very similar paper published in Material Today Physics, it was exactly a conditional GAN. The signal was dispersion relation and the image was a structure. So you can see the story doesn't change a lot. There's always something like an image and signal coming into conditional GAN, and it's doing the job for us. Well, here I want to just go into the other kind of data, talking about the graphs. So let's first see what is graph and how we can relate it into metamaterials, and then we go into graph CNNs. So talking about graph theory, it's very easy. We have a bunch of nodes or vertices, and they are somehow connected to each other using information between them. We call them edges. The edge can be anything like similarity of two nodes, distance of two nodes, or something like that. Well, we have some directed graph or digraphs in a way that one node happens after the other one. So there's a relation between happening these nodes, but sometimes we have an undirected graph. I mean, the weights or edges only show the relation, similarity or so between the nodes. And as a brief introduction to graph theory, each graph can just be shown by V and E, a set of nodes and a set of edges. It's all enough for us just to understand what's going on. So whenever you can somehow imagine that your metamaterial has a capability to be modeled by a bunch of nodes and the relation between nodes, it's all enough. You have your graph and you can work using a kind of graph CNN. So what is graph CNN? We know that in CNNs or convolutional neural networks, the input is something like an image or a signal. And we know that a process of convolution is done for many times, and we extract features, and finally we send it into machine learning algorithm like neural networks. So what happens here in graph CNN? The input is just a graph, not an image or a signal. So I have two specific characters to see how should I model them. One is pooling and one is convolution. What is pooling? If we talk about an image, after applying that convolution filter, we make it a bit smaller by averaging or something like that. This was pooling in original format. And here pooling can be a kind of graph clustering algorithm. So I have a big graph, I just make a smaller version of that by encompassing, making a kind of super nodes. And this is the pooling step, as easy as this. However, the difficult part is convolution. How can I apply convolution on a graph? Well, if I talk about the convolution on an image, we had a smaller image or kernel. It was translating, so I could move it, and then I would convolve its values with my original image. However, for graph, I don't have any translation. So what should I do? The solution is that we know from the digital signal processing that convolution can change into pointwise product if we apply Fourier transform. It's a very well-known fact. So if I can somehow model Fourier on graph, everything is solved. I need to convolve a graph with a smaller graph, a kernel. And the question is, how can I do this? By transferring them into Fourier domain. If I transfer them into Fourier domain, it's just enough to have a kind of pointwise product. And what is Fourier domain for graphs? We can easily show that as Laplacian plays the role of Fourier in signals, we can say that Laplacian matrix is exactly the Fourier domain representative for graphs. So we can easily change our graph into its Fourier transform, do pointwise product, and then come back with inverse graph Fourier transform. And this is the process of convolution. It seems a bit complicated, but it's not that bad. So finally, I have a kind of graph CNN. Therefore, I can expect that the input is this time a kind of graph rather than an image or signal. And the output can be everything, like it can work for classification of graphs, it can work for classification of nodes, or link prediction, or community detection, or embedding, or generation, anything. And they can all be used in different applications in like metamaterials. So here I just want to talk about this paper. It is the graph-based metamaterial published in 2022. And in this paper, the main story is just first how to represent my metamaterial using a graph. And they showed that they first prepared a kind of primary graph and then did some constructions, dual graph, primary phase, surface, every step. And finally, there's a crystal graph. It can be covered with shell mesh or so. But the important thing is just getting such crystal graph. The graph representation is enough for us just to use it as input to our graph CNN, as we talked about that. So what happened here is that they designed a graph CNN. the input is that graph that we are talking about. It's a version of our metamaterial represented by graph. And the output is some properties. It's a kind of regression. So it's a mechanical properties, but it can be anything as we discussed, classification or so. If you take a look into this image, it's not that easy that we talked about the graph CNN. So it's a kind of modified version. It has a kind of graph CNN for edges, and it has a graph CNN for nodes, and finally combines them all together. But it is just a kind of modification. So just consider that I need to change my graph into, change my metamaterial into some graph and apply graph CNN and get every output that I expect to get from classification, regression, anything that I'm looking for. Well, finally, I just want to concentrate on multimodal data, and let's say what happens here. So I want to say what happens if I have graphs, signals, images, data points all together, just a couple of them or all of them together, and how can I combine this information using our deep learning or machine learning algorithm? An easy step is when I have image or signal and some data points. So a very easy solution to this is that we discussed that our CNN has some convolutional layers that are responsible for extracting features. And you can see that features are a kind of vector here, that blue one. And then we were using some machine learning algorithms like neural networks on their output. So if I have a bunch of data points, why not to add them into my feature vector? I mean, the flattened output of the convolutional layers. So I have my image, the features are extracted, and I have my data points. They are actually features. So I can easily add them to each other, and all together I can send them into my machine learning algorithm. The only thing is to consider the range of data, normalization, everything that's needed. For example, if the output of your feature extraction is something in range of 0 to 1, you cannot add features and data points in the range of 100. You can ruin the network overly. But this is a very easy concept just to add such information all together. The other thing that may happen is that I have some images and some signals. What should I do now? And this is a subject that I really like. This is a subject of taking a signal as input and producing kind of information in a shape of image as output. So time frequency transforms are the best solution for such works. For example, I apply short time Fourier transform, I have a spectrogram, or I apply Wigner wavelet transform or anything in a way that one signal changing in time or space changes into a shape. In one axis, I have the same time or space, and in the other axis, I have the frequency. So I can see in which time or which space the frequency is high, low, or what happens in different areas. So this is a very good information for me to take out of my signal. And it's a kind of image, so it's not difficult to combine it with another image. I can give it as different channels of my image. What happens in RGB, for example, in color images, it's just channels. I can mosaic it and add them to each other, stitch them to each other as an input or anything else. So this is, again, another solution to add information of images and signals together. What if I have many different modalities and I would like to have my own networks for them? For example, imagine that I have some graphs. So I applied some graph CNN. I have some data points, so I applied some machine learning, and I have some signals, images. I applied my CNNs, and I would like my own networks, but I want to add the whole information to get one single output. That is the best output that I want to get from multi-dimensional data analysis. So the best way for this job is a kind of fusion. It sometimes can be used a kind of ensembler or mixture of experts, but easiest way is just seeing it as a kind of fusion. So imagine that CNN gives some vector as the feature, and graph CNN is like that, and the first layers of neural networks are like that, and we just fuse them to each other. And then we train the whole network all together. And then it is a kind of end-to-end process. I have my own inputs, I have my own networks, but the output is a wise combination of these networks, and it's expected to give me a very good result finally compared to using them one by one. Well, the whole story is finished here, and I just want to thank you very much for inviting me. And as I told you, I'm not an expert in metamaterial, and I'm sorry if I had some typos. And I will be happy to answer any questions and very open to any possible collaboration and thing.
Perfect. Thank you so much. A really wonderful introduction to the subject. So thank you so much.